Okay, let us get started. So I mentioned before, class, everyone. All right, two things I mentioned before. You're going to want to load up. Hey, shush. You're going to want to load up the class webpage. tinyurl.com, simple Bayes. From there, you can get to the two things you're going to need. One is the slides that I mentioned. The other is we're going to use a spreadsheet here. You don't need it right now, but at some point, what I want you all to do is pick a random number between 1 and 10, and in that number of minutes, I want you to click on that slide so we can spread the workload on the network out just a little bit. I think that'll help. The other thing, in a minute, we're going to load up the Jupyter notebooks, but you don't need them right now. So if you are still working on getting things set up and you're playing with Jupyter, don't play with it now, because you're going to be distracted, you're not going to pay any attention, and then when we get to the work, you're not going to be able to do it because you won't know about Bayes' theorem. So pay attention. That's right. Okay. So this is Bayesian statistics made simple. If that's not the worksheet, if that's not the tutorial you want to be in, this would be a good time to go. If you did pick this one, you made an excellent choice. It's the best tutorial. I'm Alan Downey. I teach at Olin College. I always like to say a couple of words about it because most people haven't heard of it. This is a new college just outside of Boston. We were founded about 15 years ago. Our mission is to fix engineering education. One of the ways that I'm doing that is by teaching Bayesian statistics to undergraduates. So a lot of what I'm going to be presenting to you is what I'm teaching my class starting in the fall. This is my inception slide where I have a slide of my web page which has slides on it and so on all the way down. I'm going to start out, as I mentioned, with Bayes' theorem, which is the foundation of all of this, and we'll work our way up to Bayesian inference, which is Bayesian statistics. I'm also going to be teaching a computational framework that's called Think Bayes. This is a module that I developed for use with the book Think Bayes, and it gives you a couple of classes that we're going to use to do a lot of these Bayesian updates. We're going to work on a bunch of example problems, and then by the end of this, my hope is that you will be ready to go work on problems that are related to things that you're doing in your work. And one of the things I'll be curious to hear more about is what you're interested in, if you're going to find this stuff useful. I'm also going to give you some resources at the end so that you can learn more on your own, including my own book, but also some other books that I really like. So the first thing, I'm going to derive Bayes' theorem, and I'm going to do that partly to show off, and partly because it's really a very simple idea. There's not a lot to it. We're going to prove it in about 3 slides. Once you have defined probability, it is a natural consequence of those definitions. So I'm going to write P of A, P parenthesis A, for the probability that something happens, some event, something I'm trying to predict in the future. Probability of A and B has the natural meaning. It means that both of them happen. The one you may or may not have seen before is conditional probability, and that's the probability that A occurs given that B has occurred. And often this gives you some information about whether A has become more or less likely. So now I can figure out the probability of A and B using conditional probability. The right-hand side there says the probability of A times the probability of B given A. So if you want to know whether two things have happened, you can enumerate them in either order. You can say, okay, well, in order for A and B to happen, well, either A happens, and then I figure out the probability of B given A, or it could be the other way around. B happens, and then I figure out the probability of A given B. And I claim that by symmetry, because A and B is the same thing as B and A, that those two things must be equal. So if I take these two right-hand sides and set them equal to each other, and then divide through by the probability of B, I get Bayes' theorem, which someone has conveniently made into a neon sign. Which I would like, by the way, if you all are thinking about what to get me for my birthday, this is what I would like. You could all chip in. It wouldn't be a lot. So a copy of Bayes' theorem in a neon sign, that's all there is to it. There are a couple of ways to think about what this is. So one way to think about it, we've got on the left-hand side the conditional probability of A given B, And on the right-hand side, those three other terms. This is useful as a divide and conquer strategy. So if, for some reason, the left-hand side is hard to figure out, but the three pieces on the right-hand side are easy to figure out, then you've got a divide and conquer strategy, a way of figuring out conditional probabilities. And that is often useful, but in the context of Bayesian statistics, this is what we're usually interested in. This is the diachronic interpretation of Bayes' theorem. Diachronic is Greek for through time, and it's the idea that when you get new data, you change your belief about a hypothesis. So you have, before you saw the data, you have P of H, which is the probability of the hypothesis before the data. And then something comes along that changes your mind. You do an update, and the update gets you the probability of H given D, which is also called the posterior probability. That's what you believe about the hypothesis after you saw the data. So to make this clear, I'm going to give you an example. I stole this from Wikipedia. This is the cookie problem. It says, OK, I've got 2 bowls of cookies. I'm going to tell you ahead of time that bowl number 1 has 10 chocolate cookies and 30 vanilla cookies. Bowl number 2 is 50-50. It has 20 of each kind of cookie. So you, or Fred, you pick a cookie from the bowl. It turns out to be a vanilla cookie. And the question is, what's the probability that the bowl you picked from was bowl number 1? So we're going to do this, actually, we're going to solve the same problem 3 times to make it really clear. First, I'm going to solve it using Bayes' theorem. I'm going to show you what I'm going to call the table method using that spreadsheet that I pointed out to you, which at this point, half of you should have downloaded. And then I'm going to introduce the Think Bayes computational framework, and we'll solve it one more time. So first, using Bayes' theorem, I'm going to define H and D. So H is the hypothesis that the cookie came from bowl number 1. D, the data, is that the cookie turned out to be vanilla. So that's Bayes' theorem at the top, and here are all the pieces of Bayes' theorem. What I want is the posterior, the probability of the hypothesis after seeing the data. And what I'm going to do is figure out the other 3 pieces, the probability of the hypothesis before the data, which is called the prior. I'm going to figure out the conditional likelihood of the data, and that is the probability that the cookie would have been vanilla if, in fact, the hypothesis is true. That's the probability of the data conditioned on the hypothesis. And then the total probability of the data, that's what's the chance of getting a vanilla cookie under any circumstances without regard to any of the hypotheses. So I'm going to fill in these pieces. I mentioned we're going to pick a bowl at random. I guess I didn't say it explicitly, but I should say, OK, it's a 50-50 chance that we chose bowl 1 or bowl 2, so my prior is 1/2. If, in fact, it is bowl number 1, then I know that 3/4 of the cookies in bowl number 1 are vanilla, and so I can figure out the conditional likelihood of the data. And then the third piece, now, in this problem, I can figure out P of D, which is the denominator up there in Bayes' theorem. I can figure this out directly, because I've got 2 bowls. It was a 50-50 shot. I can mentally just combine the 2 bowls into one big pile of cookies, and in total, 5/8 of them are vanilla cookies, if I combine the 2 bowls. Now, normally that's not the case. Normally we have to do a little bit more work to solve this. I'm going to show you how to do that more generally, but for this particular case, I can do it directly. So at this point, I've done the divide and conquer strategy. I want to figure this out. I figured out these 3 pieces. Now all I have to do is plug them into Bayes' theorem. Okay. So I'll do the math. I'm going to take the 3 pieces, the 1/2, 3/4, and 5/8, plug them into Bayes' theorem, and if you do the arithmetic, the posterior comes out to be 3/5. So the answer to the original question is 3/5. And this is the first way of solving it using Bayes' theorem. This is probably a good place to pause for just a second and take questions. Anything so far that you want to ask about? Good? Yes, sir. That's a great question. If you couldn't hear it, it seems like I have not taken into account the other side of it. I've written this entirely in terms of bowl 1, and it seems like I haven't said anything about bowl 2. I did in a sneaky way, which is that the probability of the data brought bowl 2 in, but it was in kind of an indirect way. When I do the table method, it'll be much clearer that it really is symmetric. But that's a great question, because that is one thing about this that seems kind of weird, which is that it seems asymmetric. So the question was, I based this on bowl 1, and if I had based it on bowl 2, it seems like I would have got a different result. I understand why it seems that way. Let me do the other method, and then let me come back to it if it still doesn't seem right. But I claim, at least for now, that this is one way to do it. This is actually correct, even if it seems funny. Let's take a look and see if we can make better sense of that. A little bit of intuition on this. So we started with a prior of 50%. We ended up with a posterior of 60%. So we are a little bit more confident that it's bowl number 1 after seeing a vanilla cookie. And there is some logic to that, because a vanilla cookie is more likely to come from bowl 1 than from bowl 2. And so it is evidence in favor of the bowl 1 hypothesis. So at least in terms of intuition, it seems to be going in the right direction. Whether it went in the right direction by the right amount, we'll find out. So let's try out what I mentioned is the table method. Hopefully you all have a copy of this spreadsheet now, and I will show you how that works. Let me go over here. Let's see what's the best way for me to do this. If you all will open that spreadsheet while I'm working here. It'll ask you, would you like to make a copy of this spreadsheet? Yes, you would like to make a copy. Okay. So the columns here, the way this works, you're going to fill in, let me make that a little bigger. You're going to fill in, when you use the table method to solve a problem like this, you're going to fill in the hypotheses. This is just text. This is for your benefit, to describe what the hypotheses are. And then you're going to put numbers in these columns. For each hypothesis, you're going to put in the prior probability. And in the likelihood column, that'll be the conditional likelihood of the data. That'll be what would be the probability of seeing these data if this hypothesis is correct, or this hypothesis. So you're going to fill in the first 2 columns, and then through the magic of spreadsheets, it's going to fill in the remaining 2 columns, and I'll show you in a minute how that all works. So, this is the paper version of the same thing. I'm going to fill this in. You should fill in your version as we go along. As I said, the hypotheses that you fill in, that's just text. That's just for you to keep track of what's what. So put something into the first column just to remind you, bowl 1, bowl 2. In this case, we only have 2 hypotheses, so just leave the other rows empty. That's fine. And before I go on, have you got the spreadsheet? Anybody having trouble with it? Anything I can help with? Where to get the spreadsheet? Yes. So everything starts here. If you go to tinyurl.com/simplebayes, or you can read the URL up at the top, that'll get you where you want to be. Okay. Next step is to fill in the priors. In this problem, we were given the priors as part of the problem statement. Other problems we're going to get to later on, you have to think more about what the priors should be, but here it's just 50-50. And then the likelihoods, you're going to fill in the conditional likelihood under hypothesis 1. And that means if it actually came from bowl 1, what would be the chance of getting a vanilla cookie? And again, that was given to us in the statement of the problem. Bowl 1 is 3/4 vanilla. So the conditional likelihood of the data is 3/4. The conditional likelihood, if it's actually bowl number 2, is 1/2. Again, given to us by the statement of the problem. You look like you're not happy with that. Oh, that's a great question. I have been using likelihood and probability almost interchangeably. In this case, that thing is both a likelihood and a probability. The difference is that probabilities are going to be normalized. They're going to add up to 1. Likelihoods are not necessarily normalized. Likelihoods are often going to be proportional to a probability, but not necessarily add up to 1. Great question, thank you. Okay, at this point, you can stop thinking. The spreadsheet will do the rest of the arithmetic for you. The way it's going to work is it's going to take all the likelihoods and it's going to multiply them by the priors, and the result is column 4, and that is the unnormalized posterior. And so if your spreadsheet has done its work, it should have filled in 3/8 and 2/8, or the floating point equivalents thereof. And then the next step is to take all of those unnormalized posteriors and normalize them. And what normalize means is to make them add up to 1. The way you do that is by adding them up to see what they actually do add up to, and then just divide through by that. So I'm going to take my unnormalized posteriors, add them up, and I get 5/8. That is the total probability of the data. That's the denominator in Bayes' theorem. And in this case, that's the number that we figured out by mentally combining the 2 bowls of cookies. Now I'm going to divide through by 5/8, and I end up with 3/5 and 2/5. 3/5 is 60%. That's what we got before. And then the 2/5, we didn't figure it out explicitly before, but there it is. That's the probability for bowl 2. So we get the same result that we got last time, but one of the things I like about this is that the symmetry is much clearer now, and this is the question that you guys were asking about. It seemed like we didn't take bowl 2 into account. Here, it's really clear that we did, and now you can see where that came into the calculation. It pops up in the total probability of the data.
Why are we manually entering the second row of column 2?
The question is, why are we manually entering the second row of column 2? The question is whether these two are going to, whether these two, did I really need to put that number in there, or could we have figured it out? We could have figured it out. The priors are going to be normalized. They are going to add up to 1. Yep, good question. Although I will say, we will see some problems where they don't initially add up to 1. They don't have to. We'll see an example in a minute. Okay, so that's the cookie problem solved using the table method. Good so far? Any questions about that? This is great. You all are doing exactly what I wanted you to do, which is jump in with questions. We have time. We're not in a desperate hurry. I would rather that we ask questions and get good understanding. Don't sit there getting confused and feel like it's going past and, oh, I don't understand what's going on. Ask the questions. Yes? Yes. The question was, the table method is just doing Bayes' theorem under the hood. It's just a calculation technique to do the same thing. Yep. Yep. And that will also be true for the next thing we do, which is I'm going to show you a computational framework for doing the same thing. And it's the same math. It's just a different way of expressing it that's going to turn out to be convenient for doing this stuff computationally. So I'm going to introduce a new kind of object, which is a PMF. This stands for probability mass function. If you've taken a statistics class, this might be familiar to you. If you have not, just think of it as a map from any possible random outcome, like the roll of a die. If you roll a 6-sided die, the outcomes are 1 through 6. And it's a map from the possible outcomes to their probabilities. So on a 6-sided die, the chance of each outcome is 1/6. Hint, it's a Python dictionary. A PMF, my implementation of a PMF is just a wrapper around a Python dictionary where the values in the dictionary are the possible outcomes. Oh, sorry, this gets confusing because of the keys and values in a dictionary. but it's a mapping from possible outcomes to their probabilities. Here's what it looks like, and you're going to have a chance to run this code in just a minute, but I want to walk you through it. You can make a new empty PMF object like that. This is going to be a D6. This is going to be a PMF that represents a 6-sided die. And then I'm going to loop through all the possible outcomes, the numbers 1 through 6. And I'm going to initially set them all equal to 1. And then I'm going to normalize it, and you'll see it all. So this is the time to jump into Jupyter. Let me do a little bit of setup here. First thing I want to do before you start playing with Jupyter is require each of you to introduce yourself to your 2 neighbors. And I'm doing this because you're going to have problems, you're going to have questions, and I want you to talk to your neighbor first. So take a minute, say hello, introduce yourselves. Thank you very much. All right, stop having fun. Back to work. I'm going to show you there are 3 ways that you will be able to use the notebooks for this class. Option number 1, which is the best one, is if you can run Jupyter on your laptop, and that way there's no network traffic and you're not dependent on wireless. So let's do option number 1 first. So hopefully you have already downloaded the repository that has my code in it. That's called Bayes Made Simple. You should be able to cd into that directory. So cd into that directory, and then run Jupyter Notebook. And whatever browser you were most recently working with, it should connect to that browser and open up a window for you. And let's see if that works for me. If it doesn't, there's a backup plan. Nah, it went into a different place. That's all right. Good. OK. If it worked, you should have the Jupyter homepage like this, showing you all the files that are in that repository that you downloaded. The only one that we need for this workshop is workshop01.ipynb. And so you can open that up by clicking on it. Definitely don't look at workshop01_solution.ipynb. That would be very wrong. And actually, I say that as a joke because I actually encourage you to cheat. Feel free, anytime you get stuck on one of these exercises, look at the solution or, hint, look at the next slide in my presentation. Okay? If you get stuck, feel free to cheat. The point of all of this is to think about it, try it, see how far you get. But if you get stuck, don't bang your head on it. Just look at the solutions, and it will all make sense. So open up that notebook, and you should be ready to run. If you run the first couple of cells, especially this cell that has all the imports in it, you'll have a good sense of whether your environment is working. I was tipped off by a Mac user that this line can create problems on a Mac if it's at the end. Apparently, we need to do it before we import the things it depends on. I think if you move it up to the top, if you're on a Mac, that should avoid that problem. And then other than that, you should be able to execute the imports. And then if that worked, you should be able to create the PMF that we were just talking about and print the initial probabilities. And I'm going to come back to this in a minute. So that is setup option number 1. Setup option number 2 is to go back to the web page, scroll all the way to the bottom, this is option 2 only if option 1 failed, and press the button. You should never press the red button. Press the red button, and it should do what it says, which is to launch Binder, which is going to be slow. So what's happening is there is a new virtual machine being spun up on a machine somewhere in Texas, I think, that will allow you to now run Jupyter on their server from your browser. The only problem now is that every time that you run these things, you are doing a little bit of network traffic. It's not a huge amount, and we should be OK. This looks like it's behaving reasonably well. So that is option 2. Option 3, if nothing else works for you, is to talk to one of those nice people that you just introduced yourself to and work with them. So if you're really stuck, I encourage you to practice a little bit of pair programming, make a new friend, and don't spend the rest of this workshop trying to get Jupyter to work. Okay? That will not be the most effective learning experience for you. So I'm going to say budget about 2 minutes to getting this working. And if that doesn't work, make yourself a new friend and do some pair programming. All right. Back to the slides. So start working through the notebook, Workshop 01. There's some text there that you can read through, run the cells, run the code that's in the cells. Do the first exercise, and if you have enough time, go on and do the second exercise. I'm going to take a couple of minutes and walk around and help people out. Let me also introduce Eric Ma, who is helping out. He's in the back there. He just waved his hand when no one was looking, but now everybody look at Eric. There we go. That's Eric there. So if you have any trouble, grab either me or him, and we will get you set up, and then we'll resume in about 5 minutes is about how long this one will take. So. Yes, I think del works. You could remove it. I think there's del, I think there's remove, but you could also just set the probability to 0. All right, I'm ready to go. So the way I'm going to work a lot of these exercises is while you're working, I'm going to do a solution up here. So if you're making progress and you don't need my help, just ignore me. If you're stuck, you can watch what I'm doing up here and see how the solution goes. Okay, let's take a look at a solution. So I mentioned that the PMF object provides an add method, and that means that when you apply the plus operator, it invokes a function that figures out the PMF of the sum. If you know some statistics, what it's doing is convolution of the distribution with itself, and what you get, the result, looks like that, and that is the distribution of outcomes for the sum of 2 dice. So the possible outcomes are the values 2 through 12, but they're not all equally likely anymore. 7 is the most likely because there are 6 different ways that you can get the 2 dice to add up to 7. 2 and 12 are unlikely because for each of them, there's only one way for that to happen. So the distribution looks like that. It's a triangle shape. Are there any questions about the first part of the solution? So this is just, I wanted to introduce you to these PMF objects so that you're familiar with them. Yes? That's a great question. Somebody else asked about that because if you are expecting it to compute the mean of the probabilities, it is very strange because the mean of those probabilities is 1.6. What it is computing is the mean of all the possible outcomes, which are adding up 1 through 6. So if you think of them all being equally likely, then you could just add up the numbers 1 through 6 and then divide by 6, and the result would be 3.5. So this is the mean outcome, not the mean probability. Did that make sense? Good. The fact that 2 people asked me that question tells me that that's something I should clarify, so that's really useful for me to know. Good. All right, and I also want to show you a solution to the second part, although I want to warn you that this is not quite correct, because one of the things I want to ask you is, why is it not quite correct? So suppose that I have rolled 2 dice and you have not seen the outcome, and I tell you that it's not a 2 and it's not a 3, that the outcome is greater than 3. And I would like you to figure out the distribution of remaining possible outcomes. So one way to do that is to set the probability associated with 2 to 0, set the probability associated with 3 to 0, and then plot the probability of the remaining outcomes. And that is very close to being correct, but not quite correct. Why is it not quite correct? You are shaking your head and frowning at me, which makes me think that you know. My probabilities don't sum to 1. Is you were going to say the same? You're exactly right. So I've eliminated 2 possibilities. I've taken some probability away from this PMF. The remaining outcomes no longer add up to 1. How can I fix that problem? I can run normalize again. So after removing the 2 probabilities, now the result is going to be disappointingly similar because the shape is going to be exactly the same. All the proportions are the same, but it's going to be a little bit higher than it was. So the upper bound of this graph is currently 0.18, and when I hit return, it will tell me that I invoked this on the wrong thing. Why didn't any of you tell me that? There we go. So this whole distribution is just a little bit taller than it was before. Yes? Great question. Is there any use for an unnormalized PMF? Why wouldn't you just renormalize all the time? The answer is sometimes you would get it wrong. If you constantly renormalize, we're going to see an example where you would get the wrong answer. Sometimes you have to perform a bunch of operations and only renormalize when you're done with all of them. Now, this example, it would have been OK. This example, I could have done the first update, renormalized, then the second update, renormalized. I would have got the same thing. I'll leave it to you to check whether that's true or not. But other cases, it would not get the same thing. Good. Anything else? Good so far. OK. Let's go back to the slides. So this structure, what we're going to use these PMFs for now is to do Bayesian updates. The way that's going to work is you're going to make a PMF object that represents your prior belief in each hypothesis. So the outcomes, instead of the numbers 1 through 6, the outcomes will be hypotheses. And the probabilities will be the prior probabilities of those hypotheses. And then you're going to go through the PMF, and for each hypothesis, you're going to multiply the prior by a likelihood, and then you're going to renormalize the whole distribution. So this is going to be Bayes' theorem in a sneaky, indirect way. And you'll get a sense of how that works. The key thing to realize is that when you renormalize a PMF, you are dividing through by the total probability of the data, which is that P of D term that's in the denominator of Bayes' theorem. So here's what that's going to look like. I'm going to create a PMF object. I'm going to call it cookie, and I'm going to initialize it with 2 strings. In this example, the way I'm going to represent hypotheses is with strings. Later on, we're going to use numbers. We're going to use other kinds of objects. You can represent the hypothesis any way you want, but in this case, it's just a label, really. It's just a string. Now, when you initialize a PMF, by default, it's going to give equal probability to all of the outcomes. So this is the initial condition. If I needed different priors, I could do it, but this is just a simple way to do it. Create the priors. Now, I'm going to take each hypothesis and multiply it by the likelihood of the data. And here's how that's going to work. I'm just going to use the times equals operator. And the likelihoods are the same that we saw before when we did the table method, 0.75 and 0.5. And then we'll renormalize. There's actually a return value from normalize. What it returns is the normalizing factor, which is the total probability of the data. In this example, we don't particularly care, but it's the 5/8 number that we saw before. And then after the PMF is renormalized, I can print it, and I get the posterior probabilities of the 2 outcomes, which are the 0.6 and the 0.4 that we saw before. So we're going to get the same answers again. So you're going to have a chance. The notebook has all that code in it, so you'll run it in just a minute. And then you'll have an exercise to work on. And that is after you do the first update. So you drew 1 cookie. It was vanilla. You did an update. Now you've got the posteriors, 0.6 and 0.4. Now, just to keep things simple, you have to put the cookie back. It's a little bit more complicated if you don't put the cookies back. And then you stir the bowl around a little bit, because this is getting kind of gross. You picked up the cookie, you licked it, you put it back, you stirred it up. Now you grab another cookie. It turns out to be a chocolate cookie. You're going to do a second update. So that's what the exercise asks you to do. So back to the notebook, run through the code for the first update, and then your exercise is to do the second update. I'll give you a few minutes, and I'll come around. I'm ready to go. Yep. All right, so again, if you're making good progress and you don't need my help, just ignore me. But if you're stuck, you can pay attention. Okay, let's take a look at a partial solution. This structure is what we're going to see over and over. When you do one of these updates, you're going to loop through, or in this case, just enumerate all the hypotheses. And for each hypothesis, you're going to multiply the current probability, which is the prior, by a likelihood. Now, in this case, the prior that I'm starting with is the posterior that I ended with. That is to say, when I did the first update, I went from 50-50 to 60-40. And now I'm going to start with 60-40. I'm going to multiply by two new likelihoods, which is the likelihood of a chocolate cookie. What's the likelihood or probability of getting a chocolate cookie from bowl 1? If I remember right from the statement of the problem, bowl 1 is 1/4 chocolate, and bowl 2 is 50% chocolate. So those are my two likelihoods. Renormalize, and then print the distribution. Question?
So I get what you've done, but it just seems weird because we know that the balls are 50-50.
Yeah.
We've just assumed that 60-40.
Interesting. Okay, so this seems weird, and I'm going to try to paraphrase just because people didn't hear the question. We started with 50-50, and now then we ended up at 60-40, and now we're at 42-57. It sounds like you're just saying, what? Okay. One way to think about this is that every time you see a new piece of data, it changes your opinion about what's going on by a little bit. We started at 50-50. We saw a vanilla cookie. Vanilla is more likely from bowl 1, so that moved us in the direction of thinking that it's bowl 1. And it moved us from 50 to 60. Now we draw a chocolate cookie, and one way to interpret your reaction to that is, you know, I thought it was bowl 1, but now having seen a chocolate cookie, I'm starting to doubt myself. And in fact, a chocolate cookie is quite a strong piece of evidence, because a chocolate cookie is twice as likely to come from bowl 2 as from bowl 1. In fact, the chocolate cookie is such strong evidence that it has tipped me all the way back past 50-50 to 42. Okay? And if you like, you can keep going and draw some more cookies and see how it goes. And that needle is going to kind of tip for a while. Eventually, once you've seen enough data, you will be nearly convinced that it's bowl 1 or nearly convinced that it's bowl 2, depending on which one it actually is. I got one here and then there, yes.
Could you just redo the hypothesis of being trying 8 chocolate and then 8 or 8 vanilla and then a chocolate?
Good question. Let me repeat that one, which is, could I reinterpret the data as being a chocolate cookie and then a vanilla cookie? And would I get the same thing? Or could I take the 2 pieces of data at once and think of it as doing a single update? And this is true for this problem and true in general for Bayesian updates. It doesn't matter what order you consider the data in. And it doesn't matter whether you break it up into a bunch of little updates or do a one big update, you will get the same answer either way. And that's actually exercise 4. We're not going to do exercise 4 live now, but if you're curious, I encourage you to poke around with it and convince yourself that what I just said is true, that you can take the cookies in the other order, or you can take the 2 cookies at once and do a single update instead of 2, same answer either way. And then I had a question over here.
Would you mind if we did the end of exercise 2 and exercise 3 again together? Or like go over them together?
Sure. Let's take another quick look at exercise 2.
Or sorry, I guess the end of
The first couple of steps. Sure. Let me just walk through this code again. So I started out by creating a PMF that has one entry for each hypothesis. And in this case, the hypotheses are represented by strings. So when I print it, I get the 2 hypotheses and their prior probabilities. And then this is what an update looks like. Yes?
curiosity, why are they initially set at 0.5? Like, did we set them at 0.5 initially?
We didn't. That's the default behavior for the PMF class. If you just give it a list of outcomes, it assumes they're all equally likely. If you want to do a different prior, you can, but that's the default behavior. And another question there.
Yeah, I just want to understand sort of the mechanics a little better. So bowl 1 and bowl 2, you're saying these are hypotheses.
Yep.
Like, what are... I guess I don't really understand the problem that well. It's like,
Yes.
trying to figure out about bowls.
Good question. I'm using a little bit of a shorthand when I say that bowl 1 is a hypothesis. What it means is it is the hypothesis that the bowl I'm drawing from is bowl number 1. I'm trying to figure out which bowl it is.
I think we need to explain that we didn't see the person choose it, so we don't know which bowl it came from.
You don't know which bowl it came from. All of this is trying to guess which bowl they got it from. Yes. Yeah. If you like, roll back into the slides, a couple of slides. The statement of the problem is all on one slide. This might be a good time to reread it just to make sure we're in good shape. Good. Thank you for asking me to clarify that. Okay. So I mentioned we're not going to do exercise 4 now. We're going to come back to, sorry, you can do that another time. Anything else about the cookie problem? Yes? How hard is it to do without replacement? The only thing you need in that case is a data structure that will keep track of how many cookies are left in the bowls. And that's actually an exercise in the book, and I have a solution to it. So if you like, I can point that to you another time. Right. The likelihoods change each time. Right. If you don't replace the cookies, then the probabilities, the likelihoods of the data change each time. So if you start out, let's say that you think it's bowl number 2, so you think it's 2020. You get a vanilla cookie, you take out the vanilla cookie. If you are right and it's bowl 2, then bowl 2 now contains 19 vanilla and 20 chocolate. And the next time you draw from bowl 2, you would need to update your probabilities. Yes?
So every time we draw a cookie, say we don't know anything about the distribution of cookies in bowls, right?
Yep.
Every time we draw a cookie, we're getting closer to the true probability that is unknown to us, right?
Sort of. You're answering a question that's coming up later today. You're ahead.
What is that called when we reach that?
Convergence. Yep. Good. Okay. So let's go back to the slides. This is the exercise that you just did with the updates, and those are the posterior probabilities. And that is all we'll do with the cookie problem for now. I want to introduce the dice problem. I think we'll have time. We'll do one more exercise, and then we get a break. So let me propose the dice problem. Suppose that I have a box of dice back here, and it contains a 4-sided die, a 6-sided die, an 8, and a 12-sided die. And I reach in there and I pick one at random, and so let's assume that I pick one with equal probability. So 4 dice, I pick one of them with probability 1/4. I roll the die, but I don't let you see which die I rolled. But I tell you that I got a 6. And then I ask you, which die do you think I rolled? Make sense? Okay. So similar to the bowl problem, where I didn't let you see which bowl I drew from, but I just told you the outcome, vanilla cookie, and you were guessing which bowl it was. Same thing here. I've chosen a die, you don't know which die it was. I told you the outcome, 6, and you're guessing which die I rolled. Good question. The 4-sided die is numbered 1 through 4. They all have conventional numbering, 1 through 6, 1 through 8, 1 through 12. Good. Okay. So I want to show you how to solve this problem using a table, and then we'll do it using PMFs. So first step, as always, is to specify what the hypotheses are. And I'm just going to write them down like that. This is a little bit of a shorthand. So 4-sided means the hypothesis that the die I rolled was the 4-sided die. And similarly for the other hypotheses. And I told you in the statement of the problem that I was equally likely to choose any of the dice. So the prior probabilities are all 1/4. And so I could put 1/4 there. But I'm going to cheat just a little bit, and this is getting back to a question I was asked earlier. I'm going to start with unnormalized priors. And the reason is I'm going to have to renormalize this at the end anyway. So I am free at any time to multiply the whole column by anything I want. And that extra factor is going to drop out anyway. So starting out with 1, 1, 1, 1, same thing as starting out with 1/4, 1/4, 1/4. Okay? I need to figure out the likelihoods. Think about this one for just a minute. What is the likelihood of getting a 6 on a 4-sided die? 0. That one's easy. So go ahead and fill in a 0. Now, what's the probability of getting a 6 on a 6-sided die? 1 out of 6. How about on an 8-sided die? 1 out of 8. And on a 12-sided die, 1 out of 12. So you can plug those in. Now, again, here's the cool thing. You don't have to think anymore. You've done all the hard part. Once you figure out the priors, once you've figured out all the likelihoods, everything else is arithmetic. I like to think that the spirit of the good Reverend Thomas Bayes, after whom Bayesian statistics are named, comes and magically fills in the rest of the cells. You might think that it's a server somewhere at Google, but it's actually. So there are my unnormalized probabilities, and again, this is just multiplication. This is just the product of the first 2 columns. In this case, because my priors are all 1s, I didn't have to do a whole lot of math there. I add them up. Before I add up fractions, I'm going to multiply them all through by 24. Just to So there are my fractions, but again, because I have to normalize anyway, I might as well multiply everything by 24 in order to make it into a nice, easy integer. Add them up. 9, divide through, and the results are 4 ninths, 3 ninths, and 2 ninths. The question was, why did that's all right, why are my priors 1 rather than 1/4? And the reason is that I wrote down 1/4, and then I multiplied through by 4. And the reason I'm allowed to multiply through by 4 is that I'm going to have to normalize at the end anyway. So whatever multiplicative factor I apply, if I multiply everything by the same number, it's going to disappear. It's really just an arithmetic hack. It's not exactly a deep, important conceptual point, but it is nice to know. It comes in handy, especially because with the likelihoods, sometimes it's not easy to figure out what the likelihoods are as probabilities, but sometimes it's easier to figure out, well, I've got something that I know that is proportional to the likelihood. It's not normalized, but it has the right proportions. Turns out that's good enough. Mm-hmm. Yes, in your spreadsheets, you're going to get numerical, you're going to get floating point numbers. But your results should be the same as mine. 4 ninths is 0.4 repeating, 0.3 repeating. Good? So there's the table method. Now we're going to use the computational framework again. I'm going to introduce one more new thing, which is a suite. And a suite is a kind of PMF. If you are used to UML diagrams, you'll recognize this UML diagram at the bottom. What this says is that a PMF contains a dictionary. A PMF has a dictionary. And now I'm defining a new thing called a suite, which extends or inherits from PMF. So a suite object will be able to do anything that a PMF object can do, plus it has some additional features. I'm going to tell you what the additional features are in a minute, but for the first exercise, you don't need them. All you need to know for now is that a suite is a PMF. Okay. Here's how my setup is going to look. I'm going to import the suite class, instantiate a suite that has 4 hypotheses, and now I'm representing the hypotheses using integers. Okay. When I print that, it'll come out to be 1/4, 1/4, 1/4. And now if you will go into the notebook and do exercise 5, and if you have extra time, you can go on and do exercise 6. Actually, even if you have extra time, don't go on and do exercise 6 yet. I want to tell you more before you do it. So the structure of all these updates is going to look the same. Every time you do an update, you're going to go through the suite, and for each hypothesis, multiply by some likelihood, renormalize, and then print the result. Pretty much the only thing you have to figure out when you do the update is what these likelihoods are. And we just figured them out. They're the ones that were in the spreadsheet. Yep, the question was, using this multiply equals is updating the existing probability. So it's taking the prior and multiplying it by this likelihood.
So it's like on the first one, I didn't update the probability, I just set the probability based on what we saw. And that would have given the same result. Well, this way, you can do it.
Correct. So again, if you're making good progress, you can ignore me. If you've got an answer and you want to see if it comes out the same as mine, you can take a look. And if you're stuck, you can take a look. D. Okay. How much sense is this making? Do people have questions? What can I help with? All right. Okay. I'm going to do one more thing, and then we're going to take a break. So let's definitely, if you have something, if you have questions, but you don't have specifics, let's talk during the break. Let me do one more. I'll go over the solution, and then we will do one more thing, and then we'll have donuts. So is it bagels? Okay. We'll have toroids of some kind. So again, I created a suite that has 4 hypotheses in it, and the default behavior is that they all have equal probability to begin with. So this suite represents my prior belief about which die it was. Initially, they're all equally likely. The update is always going to have the same structure. For each hypothesis, I'm going to compute the likelihood of the data if that hypothesis is true. And this is the magic divide and conquer part of Bayes' theorem, which is that when you are figuring out each likelihood, you can put on your mental blinders and pretend that you know which hypothesis is true and figure out the conditional likelihood of the data. So what if I told you for sure that it was die number 4? And I asked you, what's the chance of getting a 6 on a 4-sided die? You would know for sure that it's 0, and you would plug in that 0. If I told you for sure that it was the 6-sided die, you would know that that probability is 1/6. and so on for the others. And the nice thing about these blinders is that it takes a big, complicated problem and makes it into a sequence of small, simple problems. And once you've figured out the likelihoods, Bayes comes in and does the rest. It renormalizes and then prints the results, and in this case, the results are the same as what we got using the table method. Good. Okay. The reason I'm emphasizing the fact that this structure is the same every time is that when something is the same every time, you should encode it and not do the same work over and over. This is a principle of software engineering that I will now apply to doing Bayesian updates. So the suite framework that I described does this for you. You create a prior, you multiply each prior by a likelihood, and then renormalize. And the way it does that is providing this method, which is called update. So suite provides a method called update that does this. This is the framework of every Bayesian update. I'm going to loop through all the hypotheses. For each hypothesis, I'm going to compute the likelihood of the data given that hypothesis, multiply, this is the times equals thing that we've seen, and then renormalize the data at the end. Yes?
This seems like it wouldn't work. You couldn't call them full and multiple, assuming that they are meaningful inherently.
Good question. So the value that I'm going to get here, hypo, can be any type of data structure, string or integer or other kind of object. But what's going to happen is it's going to get passed off to the likelihood function, and the likelihood function is going to need to know how to interpret it. Yes. It does have to be hashable. Correct. Good question. The question is, what is normalized doing? At the end of the Bayesian update, it is adding up all of the probabilities and dividing through. In the table, that's the step where I added up the fourth column and then got that result and divided through. And in Bayes' theorem, it's the denominator, P of D. Okay. So the suite class provides update. You have to provide likelihood. Each time you solve a problem, you specify likelihood, and the suite provides update. The way you do that is by subclassing or inheriting. So I'm going to define a new class that's called dice that inherits from suite. So this new thing called dice will be able to do all the things that a suite can do, which means that it can do all the things that a PMF can do. But in addition, it also provides update, and it also provides likelihood. So your job is to fill in this function. And this is the last thing standing between you and a snack. This is Pavlovian education. So what you have to do is somebody is going to give you a piece of data and a hypothesis, and they're going to ask you, what is the probability of this data under this hypothesis? The way they're represented is that hypo will be an integer. It will be the number of sides on the die. And data will be the outcome. It will also be an integer. So in our example, data is 6. Data will always be 6. This function is going to get called 4 times. The first time it gets called, hypo will be 4. 6, 8, and then 12. Your job is to write a function that will correctly figure out the likelihood of the data given the hypothesis. So this is kind of like you are stuck in a room, and all your job is to just answer questions. Someone will say, it's a 4-sided die. What's the probability of getting a 6? And you'll say, and then the next day, you're sitting in your room, and someone will come along and they'll ask, it's a 6-sided die. What's the probability of getting a 6? And you'll say, and then the next day, little bunny foo-foo comes along and asks. They tell you, and this is the key thing to understand, which is that you are told which hypothesis is true. And then you are asked, what is the probability of the data? So if someone came up to you and said, it's the 8-sided die, what's the probability of getting a 6? You would say 1/8. Okay. That's it. That's all this function does. The reason that people find this exercise hard is that they try to do too much. Don't try to solve the problem. Don't try to figure out which die it is. All you have to do is figure out the likelihoods. Someone's going to tell you which hypothesis is true. They're going to tell you the outcome. All you have to do is figure out the likelihood of the data for that hypothesis. Fill in that function and run it, and it should work and give you the same answer you had before. And by the way, you probably want to start by just copying that. Left off, this is the exercise that you were working on, and I filled in part of the solution. Let me just recap a little bit to remind you how all this is going. We've created a new thing called dice. We've inherited from suite, and that means that we got the update function that I showed you in the slides. So you don't have to write this, but you are going to write a likelihood function, and your likelihood function is going to get called 4 times. Each time your likelihood function gets called, you're going to be given a hypothetical value for the number of sides on the dice, and you're going to be given the data, the outcome, the number 6. Your job is to fill in this likelihood function, and I've started to fill it in like this. It says, I've got a likelihood function. Someone's going to give me the data. They're going to give me the hypothesis. If the data, the outcome, the 6, exceeds the number of sides on the die, the hypothesis, that can't have happened. So this result has to be 0. Okay? So if you tell me how many sides there are and you tell me the outcome, and the outcome exceeds the number of sides, 0 likelihood. If that's not the case, then what's the likelihood of the data under that hypothesis? What should I fill in there? 1 over hypo, 1 divided by hypo. Good. And one quick Python 2 versus 3 thing that somebody asked me about. I'm using Python 2, many of you are using Python 3, but way up at the beginning of this file, you might have noticed that from future, I import the print function and division. And division means that when I do this division, even if those 2 things are integers, it's going to do true division, and it's going to give me a floating point result. So you don't have to worry about 2 versus 3. Okay, so there is this new thing called dice. Now I'm going to instantiate one of those. I'm going to make a dice object, and I'm going to update it with the data 6. And there is the result. And this is the same as what we got from the table and the same that we got from the previous. Yes?
I'm not sure exactly how the update function works. Do we need control over the negative values?
Good question. Do we need to check for the possibility of negative values? We have some control because we have created the hypotheses here, and we've created the data there. So we don't have to do a lot of error checking. You could, it wouldn't hurt, but in this case, I think we've got enough control that we can skip it. Good. Okay. And so there's the framework. We did 6. There's the solution. There's the code we were just looking at. Those are the posteriors. One nice thing about this, like the cookie problem, you can do an update, and then you take the posteriors from that update and do more updates. So if you get more data, now one thing I should be clear, this is the same die that I'm rolling over and over. So again, just to review the scenario, I've got my box of 4 dice. I pick a random die. You don't get to see which one it is. I rolled it. I told you it was a 6. You did that first update. Now I take that same die, I roll it 5 more times, and I tell you I got 8, 7, 7, 5, and 4. Now my question is, which die do you think it is now? And you can see here the answers, and you can see them in the notebook as well. So again, I'm using the posterior after I did the 6, and then 5 more rolls. So this is a total of 6 rolls. And there are the results. So the 4-sided die has 0 probability because I rolled something bigger than 4. The 6-sided die has also been eliminated, but the 8 and the 12 are still possible. And interestingly, the 8 is a lot more likely at this point than the 12. This is one of those things that a lot of people find a bit disturbing, because it seems like there's not much difference between the 8 and the 12 at this point. They're both still in the running. Why am I seemingly so convinced, 92%, that it is the 8-sided die? Yes? Because out of 6 rolls, I've never seen anything higher than an 8. And if it were the 12-sided die, that would be unlikely. Right? So if it were the 12-sided die, the data would be unlikely. If it were the 8-sided die, the data would be reasonably likely, and that's what those posterior probabilities are telling me. Okay? So I was about to say it's consistent with our intuition. Kind of. Sometimes.
That makes sense, but how does the
How does Bayes actually figure that out? Each time through, the 8-sided die is getting multiplied by 1/8. And each time through, the 12-sided die is getting multiplied by 1/12. So every single die is clobbering the 12 a little harder than it's clobbering the 8. Until, what would happen if I rolled a 10? 8 would go to 0, and that 12 would immediately pop up to 1. So one way to think about these Bayesian updates is that it's a little bit like whack-a-mole. You can think of your hypotheses as being lined up, and you're hitting them with hammers. And if you hit one of them really hard with a hammer, all the rest pop up a little bit. And if you have clobbered all of them down to 0, well, all but one, the last one has to go to 1. One thing that you should think about a little bit, what happens if the last one goes to 0? What if they're all impossible? Your assumptions are wrong. Something in your model is wrong. You started with something that wasn't true. You started with the assumption that your hypotheses were mutually exclusive and collectively exhaustive. Collectively exhaustive means that one of them must be true. If data come along and tell you that none of them are true, you've contradicted one of your assumptions. Your model is wrong. Your assumptions are wrong. Yes. What I just said is, what happens if all of your hypotheses seem to be impossible? That means that one of your assumptions was wrong. Your model of the scenario is wrong. Okay.
Could you add to the model a extremely low probability extra hypothesis
Great, that's a great question. So one of the ways to work with that is to add an extra hypothesis that is the catch-all something else hypothesis that initially has a very small probability. And it would be the my model is broken hypothesis. And you're right, if everything else gets eliminated, then that hypothesis would pop up to 1. That would not be a bad idea. Okay. The thing I'm calling the model is your assumption about the world. Right. Yeah. Now, in the toy example that I just told you, it's hard to think about how your model could be wrong. But in the real world, these kinds of models, they're always based on assumptions. And so if something breaks, you always have to go back and rethink what that was, which is actually a really nice segue. It seems like we've been doing toy problems so far, but one of the reasons that I like the dice problem is that we have, in a sneaky way, just solved a real-world problem. And I'll explain to you how this works. This came up during World War II. This is called the German tank problem. The Germans, when they were manufacturing the chassis of the tanks and the wheels of the tanks, had molds that had serial numbers on them. And those serial numbers were allocated in blocks of 100. So if you're familiar with like how IP addresses get allocated, it's kind of the same. Each factory during each month would get a block of 100 serial numbers, but they wouldn't necessarily produce 100 tanks. So they would start at 1, and then they would go up to however many tanks they produced in that month. And then at the end of the month, those unused serial numbers would go unused. Okay, so now if you're the Allies and you capture a tank, you can estimate how many tanks the Germans made by looking at the serial numbers. Because within each block of 100, you know that they made somewhere between 1 and 100 tanks. If you capture tank number 37, well, you have a pretty good indication that they made 37 or more tanks at that factory during that month. So then the question is, how should you update your belief about how many tanks they made based on that data? Well, same thing we did before. We need to figure out the likelihood of the data under the hypothesis. So now the hypotheses are the number of tanks within the number of serial numbers in that block that were used, and the data is an observed serial number like 37, and the likelihood of the data under the hypothesis is exactly the same as what we were just doing for the dice problem. In my example, everything under 37 has gone to 0 for the same reason that the four-sided die went to 0. And everything else is proportional to 1 over hypothesis, or 1 over n. Okay? And you can see in the notebook, if you want to run the next few cells, so this creates a tank object that's actually identical to our dice object. The difference is that when I create the tank, instead of just 4 hypotheses, I have 100 hypotheses for the hypotheses that the Germans might have made anywhere between 0 and 99 tanks in that serial number. And then I do an update with tank number 37 and plot the result. If you haven't run it yet, you might want to think for just a second about what you think that curve is going to look like, and then plot it. So we know that everything from 36 on down is going to be 0. What does the rest of it look like? It looks like that. So this says, if I know that the Germans made somewhere between 0 and 99 tanks, and they're equally likely to have made any number in that range, and I capture tank number 37, I am now sure that all the numbers from 36 on down are 0, and all the other numbers are proportional to 1 over n, although it's not a complete 1 over n curve, it's been truncated. And that extra probability that's off on the right-hand side there has been normalized in. So remember this game of whack-a-mole. Everything above 100 got mashed, so everything below 100 went up. That's what that looks like. Yes? Yes. So this is 1 factory, 1 month. Right, and then you would have to aggregate all those results to get a total estimate. Yep.
And could they tell? I mean, this is kind of getting into real world data. So they have a serial number. Could they tell which month it was made?
When they were captured, did they know what month that was from? I'm not sure how much information they had, other than each time they got a number, they knew which block it came from. They don't necessarily need to know which factory or which month that was. They really care about each block individually. I don't know too much about the details. So this is what it looks like after one update. One thing about this that's a little bit weird is that the most likely value is 37. And imagine you're an intelligence officer and a private comes in and says, "Sir, we've captured tank number 37. How many tanks do you think the Germans have?" You would say, "I think they have 37. It seems like an odd number. That is the most likely value, so if you had to place a bet and you tried to get the number exactly right, 37 would be your best bet, like if you were playing roulette. But more often you would want to know the average number. So the mean of this distribution is there, 62. So having captured tank number 37, the average number that you expect is now 62. And that seems like it's not a crazy estimate. Yeah? Yes, I started out by thinking that that block could have been anywhere between 0 and 99 with equal likelihood. If I've got other intelligence that lets me make a better prior, I could plug it in there. Good. All right. You all have an exercise to do, which is to do one more update. So suppose they capture another tank, and it's tank number 17. I want you to think about it first, what you think that curve should look like, and then do the update and try it out. And we'll resume in just a couple of minutes. Okay, let's take a look at a solution. So this is the first update with tank number 37, and this is the curve we were looking at before. And now I'm going to do the second update with tank number 17, and there is the result there. So a few things happened. The lower bound is the same. Having seen tank number 37, everything below 37 is 0. The fact that I saw tank number 17 doesn't really tell me much about what's going on to the left of 37. But it does influence things on the right-hand side, which is that all the high numbers have gone down a little bit, and my belief in 37 has gotten a bit stronger. And it's actually almost the same argument we were talking about a minute ago over there, which is why the 20-sided die got practically eliminated. Because if it was the 20-sided die, I would be unlikely to roll low numbers over and over. Same thing here. If the Germans had made 99 tanks, it would be a little bit surprising to get 17 and 37 and nothing higher than 50. Yes? You're getting a different number for the mean. Ah, because I ran the cell twice. Thank you. It doesn't matter whether it's 17, right. Anything below 37 is going to be the same. And so is this now consistent with what you were getting having just done the update once? Having done the update twice, in this scenario, that wouldn't be possible because you can't capture the same tank twice. But if, for some reason, I did see the number 17 twice, that is what the update would look like. And on the flip side, so now I've done 2 updates. I'm going to do a third update. Let's say we get tank number 85. Yes, Luciano. Yes, if I was worried about repeat data, I could add some logic to check, right? Good. Yeah, so the question is about making sure that I use the data for the right factory in the right month. I do need to know which block of serial numbers it came from. And that part I do know because the reality of the problem is the blocks were the last two digits, the low order digits of the number. So the high order digits would tell me which block it was, so I'm just looking at the last 2 digits. Okay. Right. All right. Let's not worry too much about the real world scenario. Let's not worry too much about error checking. Let's focus on the Bayesian stats. Yes, sir. Yep. That's a great question. So I seem to have got a very small amount of data, and then I do this update, and I've got these distributions. How confident should I be in those distributions? The answer in part is that the distributions are telling you how confident you should be in their width. If you have a big, wide distribution, it's like all the numbers from 0 to 99 with equal probability, that is a Bayesian way of saying, I don't know. A big, wide distribution is a shrug. As the distribution gets narrower and narrower, it's telling you, look, I think it's in this range, and I'm pretty confident it's in that range. So that's a great question. The confidence is encoded in the distribution. Yes? Is there a metric for that? Yeah, there's entropy. If you want to look up entropy, I'll leave it at that for now. Okay. This is the update with 85. I just wanted to show that as an example. If all of a sudden you see a big number, it goes all the way up. Everything below 85 is now 0, and you're pretty confident that it's between 85 and 100. Okay. I think that's all we're going to do with the tank problem for now. Yep. Yes, I did that to make this graph. You can plot one in gray and then plot the blue one. So this is after doing the first update. The gray line is the first update, and then the dark blue line is the second update. So as I said, this was a real-world problem. What they did during World War II is not exactly what we did, but they did solve the German tank problem. And after the war, they captured production records so that they could check to see whether the predictions had been right. And the statistical estimates were remarkably good. And the estimates they were getting from non-statistical intelligence reports were really terrible, like off by about a factor of 10. So this actually worked. And I have to tell you, I made a joke at one point when I was presenting this. And I said, well, of course, what they should do with those serial numbers is hash them so that people wouldn't be able to do this analysis. And I actually had a German student in the class at the time, and so from the back of the room, I heard him, he very amusingly, from the back of the room said, "I'll pass it on." Okay, so we did the dice problem, we did the German tank problem. And we are now going to do the euro problem. And this comes from when the euro coin was first introduced. And I forget now, this was maybe 15 years ago, I think. Somebody noticed that the Belgian coin was particularly lopsided because it had the King of Belgium, who has a really big nose, and it was kind of... And if you spin it on edge, so this is different from flipping a coin. If you flip a coin, even if it's quite imbalanced, it still comes out very close to 50-50. But if you spin a coin on edge and wait for it to fall one way or the other, it actually does make a difference. If it's weighted one way or the other, it could be biased. Somebody did this with the Belgian €1 coin. They did it 250 times and got 140 heads. And they thought that that was quite suspicious, and they got a quote from a statistician that says, "It looks very suspicious to me." So the question that we're going to answer is, given this data, 140 heads and 110 tails, what's the actual bias of the coin? What's the probability of getting heads? And I should say this is a problem. I'm borrowing this from David Mackay's book, Information Theory, Inference, and Learning Algorithms. I have a reference to this book at the end, and I highly recommend that you read it. This is the book that I learned Bayesian statistics from. I think it's great. Sadly, David Mackay just died a few weeks ago, and it's just very sad. He was about 48 years old, and it's just a shame. He's a great writer. He worked for the English Ministry of Energy for a while, working on sustainable energy. He wrote about Bayesian statistics. It's just very sad, but I wanted to dedicate at least this part of the tutorial to him, because he's done such great stuff. So let's solve the euro problem. We're going to assume that the coin has some probability of landing heads. I don't know what it is. Let's call it x. And I'm going to use the data to estimate the value of x. And this is getting, someone was asking me earlier about estimating proportions. That's really what we're doing now. One thing that I'm going to warn you about, we're going to talk in a minute about the probability that x is 0.5, or the probability that x is 0.75, and so on. Now, x is the probability of heads. So we're going to be talking about probabilities of probabilities, which means that your heads are going to explode, and it'll be a big mess. To help you avoid that, think of x as being a physical characteristic of the coin. Forget temporarily that it's a probability. So this is a coin, and it has a weight, and it has a diameter, and it has some probability x of landing heads when you spin it on edge. Okay? And we're going to estimate what x is. We're going to use the same sweet template again, which means that we're going to create a new thing called euro that inherits from sweet, and our job is to fill in the likelihood function. If we do that, the sweet framework will do the whole Bayesian update. That's all we have to do. So this is the framework that you're going to fill in. This is your next exercise. Again, I want to remind you, don't try to solve the problem. Just imagine that someone locks you in a room, and once a day, they come to you and they give you data and a hypothesis. And the data will be a piece of paper that either says H or T. And the hypothesis will be a hypothetical value for x, which will be the value from 0 to 100. And your job is to figure out the likelihood of the data given the hypothesis. So let's try a couple of scenarios. It's day number 1. 2 pieces of paper come under the door. One of them says heads, and the other one says X is 50%. Okay? Yes. So they're telling you the hypothesis. Every time likelihood gets invoked, you are told what the hypothesis is. You're not trying to figure it out, you're told what it is. So someone tells you X is 50%. They tell you, I got heads. What is the probability of getting heads on a fair 50-50 coin? 50%. Okay? It's a divide and conquer strategy. The magic of this whole thing is that you've taken a big complicated thing and you've boiled it down to very, very simple things. It really is as simple as it seems. Day number 2, 2 pieces of paper come under the door. One of them says, it's heads. The other one says, X is 75%. What's the probability of the data, heads, if the coin actually has a 75% chance of yielding heads? Well done. Day number 3, piece of paper comes under the door. It says, it's tails. And X is 66%. 34, close enough. Good? All right. That's your job, is to fill in a function that does what you just did. Just one slightly tricky thing. The thing you return has to be a probability between 0 and 1. The X, the hypothesis that you get, is between 0 and 100. So you need to do a little bit of math. Off to the notebook and fill that in. Okay, I'm going to put a solution up here. Again, if you're making good progress and you don't need my help, you can ignore me, but I'll talk through what I've got so far. Again, when they give me the hypothesis, it's from 0 to 100. The thing that I return is supposed to be a probability, so I'm going to divide through by 100. So x is whatever the hypothetical value is, divided by 100. If I get heads, I'm going to return x. And if I get tails, I'm going to return 1 minus x. And that's all there is to it. Good? Making sense? Let's take a look at how it all works, what the results are, and then we can come back and take another look at it if that's useful. So I'm going to start out again by creating an instance of this new class. So I'm going to make a Euro object that represents the hypotheses from 0 to 100. So that's the range up to 101 because of the Python thing where the end of the range is open. And then plot what that distribution looks like. Initially, it's uniform. Now we're going to come back. A couple of people asked me about these prior assumptions. I'm going to come back later and ask whether that's a good assumption. But for now, I'm going to keep it simple, uniform distribution. So anything between 0, meaning that it has no probability of being heads, so it's a two-tailed coin, and 100, always heads, and anything in between. So it could be a 99% coin, meaning it's so lopsided that 99 times out of 100 it lands heads. All right. I'm going to do my first update with heads. So remember, I started out thinking that anything from 0 to 100 is equally likely. When I see my first heads, that immediately eliminates 0 from contention. And now the question is, well, what does it do to all of the others? It looks like that. So that's what it looks like having seen 1 heads. Actually, I'm going to switch over to my slides just to make it a little easier to present these. So that's what it looks like after 1 heads. The possibility that x equals 0 has 0 probability. I have eliminated that possibility. The 50-50 hypothesis, okay, it could be true. But the possibility that this is a two-headed coin is starting to seem at least plausible. And this is what Bayes is telling me I should believe after seeing 1 heads. Let's say I spin it again and I get heads again. It's going to look like that. So 0, still eliminated, but even like 1 through 10, 1 through 10 are not exactly 0. 1 through 10 are still possible, but at this point unlikely. And all the 90, 95 is looking quite plausible. Does that curve look familiar to anybody? Do you know what shape that curve is mathematically? Now notice the first time I did this, I multiplied by x and I got a straight line. And then I multiplied by x again. That'd be x squared. That's a parabola. So now let's say I see tails. What do you think it's going to look like? Well, it's going to be cubic. That's one thing I know. The other thing I know is that the right-hand side of that needs to come down. I'm going to need to bend this down to 0. Because now that I've seen tails, it's not possible that x is 100%. It can't be a two-headed coin anymore. And so it ends up looking like that. Okay? 0 has been eliminated. 100% has been eliminated. Things in the middle seem possible. Where do you think the peak of that curve is? What do you think the most likely value is? 66%, 2/3, which is the observed proportion of heads. And that will be true in general. The peak of this curve will always be the observed proportion. But the width of this curve is telling me how confident I should be in that. Having only seen 3 flips or spins, and having seen 2 heads and 1 tails, If you force me to guess, I'm going to say 66%, but I'm also going to tell you that I'm not at all sure, which is why this distribution is so wide. As I see more and more data, it will get narrower. So let's say I've done 10 spins. So now I'm starting over again from scratch. So forget about those 3. Now I'm going to do an update with 10. Let's say that I've seen 7 heads and 3 tails. It's going to look like that. The peak is at 70%. Again, that was the observed proportion, but the distribution is narrower now, telling me that having seen 10 results, I'm starting to think I might know what x is. I'm pretty sure it's not 20 or less, but in the range from about 40 to about 90, it's still possible. And now, if I do the actual update that we were asked to compute, I got 140 heads and 110 tails. I'm going to do a little bit of Python magic here to make a string that has 140 copies of h and 110 copies of t. And then I'm going to loop and do those updates. So this is after 250 updates, it looks like that. The peak is at 56%, which is the observed proportion, and the distribution is narrow, telling me I'm pretty sure it's not below 45, and I'm pretty sure it's not above 65. Yes? The question is, having seen so much data, you would think it would be narrower than this. You would think we would be more confident about 56. Yeah, I kind of have the same feeling because it does seem like we've seen a lot of data, but this is, in some sense, correct. This is what Bayes is telling us we should believe about x. One of the reasons that it's wider than we expect is because of the square root rule, which is that in general, the width of this distribution gets smaller as the square root of n, or 1 over the square root of n. And that's, if you are thinking it should be dropping like n, and it's actually dropping like the square root of n, it'll be slower than you expect. And that's part of the reason our intuition isn't right. Yeah? That's such a great question. It's almost as if you read my next slide. Oh, actually, I take it back. It's not my next slide. I withdraw my accusation of malfeasance. I had one other thing I wanted to say about this posterior, and then I will answer that question. Thank you. This is the posterior suite. It represents what we should believe about x, having seen the data. One way to present it is to just present that whole distribution. And often that is the best way to represent your knowledge because it's a complete description of everything you know. But it's also useful to summarize it. A couple of ways that you can do that. The suite class provides mean, maximum likelihood, and a credible interval. The mean is the posterior mean, same as what we saw with the tank. The maximum likelihood is the peak, the value that has the highest posterior probability. And the credible interval is an interval, in this case, that contains 90% of the probability. Okay. And so we can run those in the... So the posterior mean is the 55.9, which is just a little bit different from the 56. So the 56 is the maximum likelihood. That's the observed proportion. So the peak of that curve is 56. The mean comes out at very close to 56. And then the posterior credible interval is a range that has a 90% chance of containing the true value. So having seen the data, you could say, I believe that there is a 90% probability that the true value for x for this coin is between 51 and 61. Eric. Yes. So what I said is that the credible interval is an interval that contains 90% of the probability density or probability mass in this case. But it's not unique. I could shift it back and forth, and so you might want to choose the one that you want. And one of the ways to specify which one you want is along the lines of what you were saying. Good. Okay. One other thing I want to say about credible intervals. How many of you are familiar with confidence intervals in classical statistics? Seen confidence intervals. Okay. If you learned about confidence intervals, one of the things that you are beaten over the head with is the idea that you cannot say that there is a 90% chance that the true value falls in a confidence interval. In classical statistics, that is a forbidden thing to say. Instead, you're told how to interpret confidence intervals, and to be honest, it's just awful. One of the nice things about Bayesian statistics is that the outcome of a Bayesian analysis lends itself to the natural, useful interpretation of probability that you want. And one of the things that you are allowed to say is that the 90% credible interval has a 90% chance of containing the true value of whatever it is you're trying to estimate. It's beautiful, it's simple, and it's useful because it allows you to answer questions you care about and make decisions under uncertainty. If you have to place bets based on the outcome of this analysis, Bayes will give you probabilistic information, probabilities that you can use to place good bets. And that's true if you're literally making bets like gambling, but it's also true anytime you are obligated to make a decision on the basis of imperfect probabilistic information. So this is one of the very nice things about Bayesian analysis. Yes?
How do you relate the Bayesian description to the description in that column that you quoted, that 7% chance of has extreme likelihood?
Right. So going back to the original statement of the problem, the statistician that they talked to said, if that coin had been fair, there's only a 7% chance that it would have produced such an unusual outcome. What that person was implicitly doing was computing a p-value. And that p-value came out to 0.07, which is considered borderline statistically significant. So he said it was very suspicious. That was his way of summarizing that. The Bayesian response to that is mostly, well, there are two responses. One is if you really want to do hypothesis testing, you can do Bayesian hypothesis testing and compute the probability that the coin is fair. Now, in order to do that, you have to be careful about specifying the alternative. Like, if it's not fair, then what? But if you do that, then you can do Bayesian hypothesis testing. But the alternative is try to avoid making binary decisions about the world. You don't have to say it's fair or not. What you can do is say, look, here's what I know about the coin. Having seen the data, this distribution represents my knowledge. And if you now have questions, I can answer them. If you want to know the probability that the next coin will yield heads, I can answer that question. And similarly, I can generalize to lots of related questions. So if you want to do Bayesian hypothesis testing, you can, but usually a better thing is to just avoid yes-no answers. Think probabilistically. Okay. Now, I said a minute ago that one of the nice things about Bayes is that the posterior distribution has the natural interpretation that you want. However, there's a price to pay for that, and it's the prior. And this is what we were talking about a minute ago. I assumed that any value from 0 to 100 was equally likely, but that really doesn't seem to be consistent with what I know about coins. So think about, actual coins. They can be somewhat lopsided. I can entirely believe that if I spin a coin on edge, it might land heads 49% of the time, or 51, or 40, maybe 40, 60, I don't know, maybe 99. It would probably be a pretty funny looking coin. 1, probably not. So my uniform distribution, my uniform prior was probably not a very good choice. A better thing to do would be to take advantage of the background knowledge that we have. This is called an informative prior. It says, look, take what you know about the situation and try to encode that knowledge in the prior, and then see what you get. So here's one possibility. This is a little bit better than uniform. This says, I think that the values in the middle, this green curve, says, I think 50-50 is pretty likely, and values that are close to 50 are pretty likely. I think 0 and 100 are impossible, and it looks like that. Yes? This is like a prior to my prior. No, this is choosing a prior. This is the first step. I do need, and I need to, sometimes it's a debate between people.
You're already making like assumptions about things that you might have observed without actually.
Yes, I'm making assumptions, but I haven't looked at the data yet. And this is, I do need to be careful to make sure that when I pick my prior, I'm not implicitly using the data. I'm allowed to use things that I've learned in life. I'm allowed to use physical models of coins. I'm allowed to say, look, I've seen lots of coins. I know what coins are like. And I can encode that knowledge. But I'm not allowed to use the data, the 140 heads and the 110 tails. Now, I know that this sounds totally bogus. It looks like I'm just making stuff up. And that is partly true. However, there is one nice thing that happens, which is I can run the same analysis with several different priors. If you and I don't agree about the priors, let's say we're having a big fight, and you say, blue, it's uniform. And I say, you're wrong, it's green, it's a triangle. One of the ways to resolve our debate is you run your analysis, I'll run mine, let's see what the posteriors look like. For this example, this is what the posteriors look like. This is your blue curve and my green curve on the same graph. And if you look in the upper left-hand corner, there's a little bit of green showing up there. But at this point, you and I could just shake hands and say, look, we don't completely agree, and actually we never will. No amount of data. If you start with different priors, no amount of data will ever get you to converge completely, except for a couple of unusual cases. But look, we're close enough that we can go have a beer. And our confidence intervals would be very close to each other, yeah. Okay? So this is one of the things that you can console yourself when you think about the priors, is that if you have enough data, reasonable people will converge. And I have to qualify what reasonable means, which is that you can't start with 0. Okay? And if you think about the mathematics of doing a Bayesian update, every time you multiply, multiplication, if you start with 0, you're going to end with 0. Okay? But if you start with some very, very small number, eventually the data will persuade you one way or the other. Okay? And this is called Cromwell's rule. It says try to avoid starting with priors of 0. You can make up arbitrarily small numbers, 10 to the power of negative 150. That would be okay. Eventually, data could persuade you. This is from, the reason it's called Cromwell's rule is his impassioned speech to Parliament. I beseech you in the bowels of Christ, think it possible you may be mistaken. Which is maybe a little bit overwrought, but it's good advice. All right. Let me pause there. So that's the end of the Euro problem. And this is, in general, how you estimate proportions. If you think that there's a physical process that yields some proportion of heads and tails or any two outcomes, it can also be generalized to multiple outcomes. This is how you do that. Questions about the Euro problem? Yes? So you're asking about my claim that the prior is not important as long as it's not 0, if there's enough data. So I'm glad you asked, because I want to make a related point. If you and I disagree about the prior, there are two things that might happen. If there's enough data, we will converge to the point where we're so close to each other that we don't care anymore. And that's a good case. That's called swamping the priors. The other possibility is that we don't converge, and in that case, the difference is telling us something about how certain we should be about the result. So in a small data scenario, you may well want to run several different priors and describe them as a way of saying, you could think of it, if you're publishing a paper, instead of telling people what they should believe, you could tell them how to do the update. And look, if you start with this prior, here's your posterior if you start with a different prior. Yeah? Could you flip it on its head and make a statement about how likely each person's priors are? Given the data, yes, you could. And that is related to what I was saying about Bayesian hypothesis testing, which is that we can do model comparison. If you start with a prior and I start with a prior, we both do an update, we could continue to disagree with each other, nicely, of course, but we could also say, you know, that data that we just saw was not very compatible with your model, and actually it was pretty good under my model. So if we're trying to balance between the two of them, we're in some sense doing a meta update about those priors. Yeah. Good. All right. We are going to take a 5-minute break just because I know it's kind of we got to have donuts, but I think it's really good to stretch out a little bit. We will come back and we will do the World Cup problem. So you can read about that if you like. We'll be back in 5 minutes, but let's make it 5 minutes sharp, please. All right, we'll get started in just a minute or two. I'm going to stall for just a minute while we're waiting for a couple people to come back. And I'm going to stall by making fun of Luciano Romaglio, who was in the back of the room. But I suspect that he's not going to come back for this next part because he's from Brazil. And the problem I'm working on is from the 2014 semifinal match, which was Germany versus Brazil, which is possibly the most humiliating World Cup match ever. How many people saw it or were aware of it when it happened? The final score was 7-1, I believe. And so this ended up being an interesting Bayesian question, which is, say you're watching the match, and after 11 minutes, the Germans score, which, wow, that's pretty early in the match. That's unusual. And then 12 minutes later, at the 23-minute mark, they score again, and you think, well, maybe this is some kind of joke. Maybe something strange has happened. So the question is, can you do a Bayesian update that would allow you to make a prediction about how many more goals Germany is likely to score after now having seen this data? Luciano, if you don't mind, I was just suggesting that you might not want to stay for this. You'd left in the middle of the game. You were actually there at the game? Yep. Oh. Oh, that's terrible. Well, I'm sorry to make you relive the nightmare. Okay. So, getting back to one of the questions we were talking about earlier, which is modeling the physical world, you almost always have to make decisions about simplifications. What can I leave out? What can I include? In this case, I'm going to model goal scoring in a soccer match as a Poisson process. And this is actually based on some statistical analysis in which people asked, does this seem to be at least approximately true? And one way of asking that is, if it is a Poisson process, one of the things that means is that a goal is equally likely at pretty much any time during the game. So the number of goals that get scored at the 10-minute mark or the 20-minute mark or the 30-minute mark is about the same. And one way to model it is to say that each team against a given opponent will have some model scoring rate, the number of goals per game that they can score against that team, and their chance of scoring during any given time interval is the same. And that's what a Poisson process is. So a Poisson process means that events are equally likely to occur at any time, and you have an arrival rate. An arrival rate means the goal scoring rate, which I'm going to use lambda, it's a convention to represent that using lambda. If it is a Poisson distribution, a Poisson process that has two consequences, it means that the time between events is distributed like an exponential distribution, and the number of events that get scored during any given time interval is distributed like a Poisson distribution. If you have done some statistics and you are familiar with those two distributions, great. If you are not, that's okay. I will explain to you everything that you need to know in order to solve this. I will say this one requires a little bit more math, a little bit more working with these statistics than the previous problems. So put on your thinking cap, hang on for another 40 minutes. We stop at 12:20. Hang in there, do your best. If this problem makes your head explode, don't worry about it. It's mostly just fun. Do your best. Okay. So here's how this is going to work. We're actually going to do two steps. We're going to do an estimation step and then a prediction step. In all the previous problems we've done, we've just done estimation. We haven't done prediction. So that's the new part in this problem. So we're going to use the data to estimate lambda. We're going to have a posterior distribution about lambda, and we're going to use that to make predictions. So thinking about this from a Bayesian point of view, this is your Bayesian checklist when you start to think about a problem, which is what are the parameters that describe this? So for the euro coin problem, the parameter was x. We were trying to estimate the probability of heads. So in the soccer problem, what are the parameters? What are the hypotheses about those parameters? And what prior information do we have in order to input into the whole process. So for this, I'm going to suggest one model, and I want to emphasize again, these are modeling decisions. Reasonable people could disagree. I'm going to say that each team, as I said a minute ago, has a goal scoring rate against a given opponent, which I'm going to express using lambda in units of goals per game. The hypotheses will be the range of possible values for lambda. So in the same way that x could be any number from 0 to 100, lambda can be any number from 0 goals per game to 100 or 1,000, or actually there's no real upper bound. Other than as a practical matter, what's your best guess? So, World Cup teams, good soccer teams. So this isn't like, Germany versus a bunch of 10-year-olds. Although, did you see the two guys against the 55? Yeah, that was good. I think if you Google soccer 2 versus 55, you will get the video of two world-class soccer players against 55 10-year-olds. It was pretty good. Okay, but thinking of two decent teams against each other, what do you think is the maximum goal scoring rate that's plausible per game, goals per game? Eric, 5 goal scoring rate. Best versus worst? Okay, like a rate of about 5. So maybe like 10 on the outside, 20 just doesn't seem reasonable. Okay, so you immediately have some prior ideas about what this could be. Where else, what could you do to get a better idea of what the goal scoring rates would be? Ask sportscasters, right. And that is one way of constructing priors is by interviewing experts. And this comes up quite a lot. A lot of times there's some work that you have to do in order to get people who are not necessarily technical statisticians to answer questions about probability. Sometimes you have to trick them a little bit to elicit information in quantitative form. But interviewing experts is one common, useful way to assemble priors. Stats from previous games is another possibility. You could say, you've got, I assume data from the beginning of time. And you could say, look, based on previous competitions, I can make a pretty good guess for the range of lambda. And that's kind of what Eric was doing informally. Okay, what I'm going to do, I'm going to use a gamma distribution to describe the distribution of lambda. Don't freak out too much about the gamma distribution. This is just a way of drawing a curve that seems to have about the right shape and about the right mean. So I went and I got a bunch of statistics, and the mean was 3 point something goals per game. And so that, for my prior, is what I did. So this is a bunch of code. Again, the details of this are not super important. All I'm doing here is constructing a gamma-shaped distribution by evaluating this function. That function is the PDF of the gamma distribution. I'm taking advantage of the gamma function that's provided by SciPy. And this is going to evaluate the PDF. This is going to make a PMF object that has the right shape. Again, if this is familiar stuff and this is making total sense to you, great. If not, the point of all of this is that it looks like that. That's all. And I forget actually what the mean is. It's not 3. That sounded too high when I said it. I forget what it is, but let's just say I looked up the number and a 1.3. That's why I was thinking 3. It's 1.3. So this is the average. 1.3 is the average number of goals per game. And so this is my initial belief about what lambda might be. It's remarkably consistent with Eric's intuition that values greater than 5 are quite unlikely. But 0, 1, and 2 are very reasonable numbers. Yes? Great question. The lin space that I'm using there is all the values from 0 to 8, and there are 101 of them. So I've taken this range, 0 to 8, and chopped it up into 101 pieces. Good. All right. So all of that was me doing background work, throwing around distributions. Your job is much simpler. I shouldn't say simple. Still not easy, but simple And this is, again, the scenario where you're locked in a room, and someone is going to tell you the hypothesis, and they're going to tell you the data, and your job is to fill this in. So bear with me for a minute, because this is going to take a little bit of explaining, which is the hypothesis that you get will be the goal scoring rate. So someone will tap you on the shoulder and say, Germany versus Brazil, their actual goal scoring rate is 2 goals per game. And then the data will be the 11 minutes. So after the first goal, you say, hey, they scored after 11 minutes. So the inter-arrival time was 11 minutes. And now your job is to figure out if the goal scoring rate is actually two goals per game, what would be the probability of seeing an 11-minute gap between goals? And the answer to this question, according to Poisson, is the exponential distribution. So this function allows you to answer that question. X is the data. X is the observed interval between goals. Lambda is the hypothetical goal scoring rate. So if I give you lambda and I give you X and I ask you what's the probability of the data under this hypothesis, that is the answer. Yes. Great question. You do have to be careful about the units because I did a kind of a weird thing. The data are in minutes. The rate, lambda, is in goals per game. So you need to know how many minutes per game. And the answer is 90. We're going to ignore injury time because it's stupid. Okay. So I'll pause there, and again, your job is to fill in this function using this information that I have provided for you. And if you go over to the spreadsheet, the notebook, there's your prior, and here's where you're going to fill in the solution, and I will get you started. So there's some starter code there if you want to work with that, and I'll come around and help people out if you have questions. Just got a great question that might help, which is we're doing one update per goal. So imagine you're watching the game, they score the first goal after 11 minutes, and you're going to do an update where X is going to be 11 minutes divided by 90. Okay. So you're going to do your first update after the first goal, and then in a minute we're going to do a second update after the second goal. For the second goal, the inter-arrival time will be 12 minutes. Here's an experiment you might want to run that will help you get a clear picture of what's going on here. Your likelihood function is going to get called 101 times. Each time it gets called, you're going to get the same data, 11, and you're going to get a different value of hypo. So I've added a print statement here that prints the data and the hypothesis. For now, all of my likelihoods are 1, so this update is not going to work. This update won't change the prior. But when I run it, it is going to print the data and the hypothesis for each run. Let me do that. So there's the prior. Here's the update. Each line corresponds to your likelihood function getting invoked once. Every single time it gets called, data is 11. And each time it gets called, you're going to get a different value, which is the hypothetical goal scoring rate in goals per game. I notice that they're not in order because this is a Python dictionary and the order is. Okay. If you're stuck, I've got a solution up here. You can take a minute, type this in, run it, run the 2 updates, and then I'll discuss it in just a couple minutes. Okay, let's take a look. So this is my likelihood function. The first line is just doing unit conversion. I'm just translating x from minutes to units of games. So it'll be 11 out of 90. It'll be about 1/9 of a game. And now the probability of scoring after 11 minutes, if the goal scoring rate is really hypo, is given by this function, lambda e to the minus lambda x. So pretty much what I did is translate mathematical notation into Python notation. Lambda is hypo, so I've got lambda times e to the minus lambda x. And that, again, thinking in terms of the Bayesian blinders, once you've computed the likelihood function, Bayes, the whole framework, comes in, calls your likelihood function 100 times, and asks, how likely would that be, 11 minutes, under each hypothetical goal scoring rate? And you can imagine that if the goal scoring rate is really low, 11 minutes would be very surprising. If the goal scoring rate is kind of high, 11 minutes would be less surprising, and so on. And that's what the distribution will look like when we do the update. So here's the prior. And again, this is based on previous games. And then here's the update. The gray line here is the prior. The blue line is the posterior. So having scored after 11 minutes makes us shift the distribution to the right. Don't be worried too much about the height. The height of these things is just a consequence of normalizing. So if it's taller, that means it's a little bit more compact. And if it's lower, it just means that it's wider. The height is not important, but the location is important, which is it has shifted to the right, meaning having seen an early goal, we are more inclined to believe high values of lambda. Before we saw the goal, 2 was quite unlikely. Now, having seen the goal, 2 is looking like a real possibility. And in fact, 5 is starting to look like it's not out of the running. You keep watching the game. 12 minutes later, Germany scores again. You do a second update. So there's the 11, and this is the 12. And again, the gray line is the prior after the first goal. So this is showing the difference between after the first goal and after the second goal. Again, the distribution has shifted to the right, and now 2 is looking like it's the most likely value, and 5 is really not all that surprising anymore.
Is the probability of 5 the area under the curve between 0 and 5?
So the area under the curve from 0 to 5 would be the probability that lambda is somewhere between 0 and 5. The probability that it's exactly 5 is kind of arbitrarily infinitesimally small. But if you give me a range, like 4.5 to 5.5, then I can compute an area under the curve. Yeah?
At this point, we know there have been 2 goals,
Yes.
but we have a non-zero probability that there's a, and that's just
Yes.
prior.
Kind of. Now, one thing to be very careful here is that the x-axis here, let me repeat the question in case people didn't hear it. We already know that there have been 2 goals, so it seems like everything below 2 should be 0, like it was in the tank problem and in the dice problem. But remember that the x-axis here is the goal scoring rate, not the number of goals that have been scored. So it is still possible that the goal scoring rate is like 0.1. In other words, on average, Germany will score 0.1 goals per game, but they've been spectacularly lucky so far. So it's still possible that the goal scoring rate is low. It is not possible that the goal scoring rate is 0. So 0 has been eliminated. Yes?
What we've done has no idea how long the game is, right? So it's sort of like an infinite game. You're just taking a slice.
That is correct. Nothing we've done so far depends on how long a game is. This is a goal scoring rate in an infinite game. If they played against each other forever, how many goals per unit time would get scored? Okay. And this is a good segue to the next question, which is now we want to make predictions. Now we want to say, for the rest of this game or for the next game, how many goals will get scored? And let's start to think about that problem. Okay. So you did the exercise. Remember I said that there are going to be 2 steps. We're going to do some estimation, and then we're going to do some prediction. We're finished now with estimation. That posterior distribution tells us what we should believe about lambda, the goal scoring rate. Now we want to make predictions. All right. There are 2 ways to do this. One of them is easy to understand and wrong. The other one is hard to understand and right. We're going to do them in that order. So option number 1 is to say, if I know exactly what lambda is, if you tell me that lambda is 2 goals per game, then I can make a predictive distribution for how many goals they will score in their next game, or in the remaining 67 minutes, whatever it is. Okay, I can make predictions. And that will be a Poisson distribution. Then if you know the arrival rate, then you can make a prediction about how many arrivals there will be in a given unit of time. Again, if that's familiar to you, good. If not, I'll show you how it works. So if we know lambda, we can make predictions. The problem is that we don't know lambda. We have a distribution for lambda. So one possibility, which is simple and wrong, is to take the mean of that posterior distribution. Okay? And if I remember right, in ours, what does that work out to be? I forget what the mean is. Did I compute it? There it is, 2.6. So I started out at 1.3. Before I saw any goals, I thought that the mean of lambda would be 1.3. Each time I see a goal, I increase it. And having seen 2 goals in 23 minutes, I now think it's 2.6. I think that Germany versus Brazil will score 2.6 goals per game on average. And now I'm going to compute the predictive distribution, which is a Poisson. And I'm going to use make Poisson PMF, and that is what it looks like. So if the average goal scoring rate is 2.3 goals per game, then on average, 2 is quite a likely outcome. 1 is also quite likely. 0 is possible. 3 is possible. 4 is less likely. 5, 6, unlikely. Intuitively, does that make sense? Okay. So if you wanted to do a quick, dirty, approximate answer to the question, this would be it. I estimated lambda. I took the posterior mean, 2.6, and I computed a Poisson distribution that takes into account the remaining time in the game, the hypothetical goal scoring rate, and this is the set of possible outcomes for the number of additional goals that they will score and the probability of those outcomes. Good? Questions about that? I say that because I'm about to make it harder. What is the 10 upper bound? Great question. I arbitrarily cut the distribution off at 10 because it was so unlikely at that point that it was essentially 0. Good? All right. However, option 2 says, you know, I don't really know what lambda is. Taking the mean is approximately right, but not quite correct. What I really should do is enumerate all the possible values of lambda and compute a Poisson predictive distribution for every possible lambda. And then I'm going to make a mixture of all those distributions. So the result is actually a mixture of Poissons, mixture of Poisson distributions. Here is visually what that looks like. Is I'm going to loop through all the lambdas in the posterior distribution. And for each possible value of lambda, compute the predictive distribution. So if lambda is actually 1, then I'm going to get a predictive distribution that looks like that. If lambda is actually 2, I'm going to get something like what we saw a minute ago, which is one of those guys. What I've shown in the graph here is one curve per possible value of lambda. And now I'm going to add them all up. But I can't quite add them all up. I have to compute a weighted sum, because some of those curves are more likely than others. The likelihood of each curve is proportional to prob, which is how much I believe that that value of lambda is correct. All right, so I'm throwing in this whole thing at the end of a 3-hour tutorial when your brains are exhausted and you want nothing more than lunch. I'm showing it to you just so you're familiar with it. If it just makes your brain hurt, that's okay. But I just wanted to show it to you. Graphically, this is what I'm doing. In code, this is what it looks like. I'm going to loop through all the lambdas. I'm going to make a predictive distribution for each lambda, and then this function adds them up. And it adds them up in proportion to how likely each curve is. Question is, why did I increase it to 15 or 14, 15? I wasn't even being consistent about it. It's an arbitrary choice. As long as it's big enough that the probabilities out there are small, it will be okay. The point of all of this is that this is what those two options look like. The first one I said was simple and wrong, where I took the mean value of lambda and I generated one Poisson distribution. And this, I took the whole distribution of lambda, all the possible values that lambda might have. For each one, I generated a Poisson distribution, and then I computed the weighted sum of those distributions. And that's what I got here. Visually, what's the difference between those? What does it look like? Longer tail. That's a good way of describing it. Here, the tail goes off to the right more. So like 8 is barely visible here. It's not impossible there. Tail is a lot longer. The probability of 0 is substantially higher here than there. In general, this distribution is wider than that one. The reason is that this distribution reflects my uncertainty about lambda. It's possible that lambda is quite low, in which case 0 is quite likely. It's possible that lambda is quite high, and in that case, values like 6 and 7 are more likely. So the correct answer, the one that correctly captures my uncertainty about lambda, is a wider distribution, because now there are, in some sense, two sources of uncertainty. I'm not sure what lambda is, and even if I was sure what lambda is, I would not be certain about the outcome of any given game. And if you take those two uncertainties and put them together, you get a wider distribution. Okay. I mention that because many Bayesian problems consist of those two phases. You start with a prior, you do an estimation based on data, now you have a posterior that represents your uncertainty about the parameters. Then you do a predictive step that represents your uncertainty about what will happen in the future based on your estimates. And that's what we saw in this example. That is the hardest part of the whole tutorial, so I hope that didn't hurt your heads too much. Any questions so far? This is summarizing what I just said a minute ago. Sure. So when you do the estimate, you end up with a posterior that represents your belief about the parameters. And so like in the coin problem, the parameter is x, and so you have a distribution of x. If someone now asks you to make a prediction, you would make a prediction about the next coin toss or the next 100 coin tosses. And your prediction would reflect two sources of uncertainty. I'm not sure what x is, and even if I knew it for sure, I still wouldn't know what the outcome of any given coin toss would be. Same thing here, I don't know what lambda is, and even if I knew lambda, I wouldn't be sure about the outcome of the next game. How did I get lambda? Did it come from the data? Yes. So my belief about lambda comes from doing the Bayesian update. I start with a prior, I see some data, and now I have a belief about lambda. Good question. Did I use data from Brazil and Germany, or did I use it in general? I used general data to get my prior. I used the history of World Cup matches. And then I used the data for the update was the inter-arrival time for the first 2 goals, 11 minutes and 12 minutes. And I used the general prior because I didn't have enough prior data about specifically Germany versus Brazil. Exactly right. You got it. Good. Okay, so we did a dice problem, which you can think of as estimating counts. If you want to know how many of something there are, it often has the structure of something like a dice problem. We did the Euro problem, which is estimating proportions. That kind of thing comes up all the time. I mentioned if there are 2 outcomes, just heads and tails, that's a very common problem, or multiple outcomes. You can generalize what we did to handle multiple outcomes. And then World Cup problem, estimating rates, arrival rates, clicks on a web page, those kinds of things. There are a lot of real-world problems that correspond to estimating rates. A few more things. So we have just 8 minutes before we are done. You can turn your brains off. You have no more exercises. You will not learn anything else today. Breathe, relax. In the remaining few minutes, I just want to tell you a little bit about how what we did today fits in with the bigger picture of Bayesian stats. I'm going to point you to a couple of resources. I will have time for questions as well, although maybe we'll wrap up and then I'll take questions. And then the last thing, we have a survey that we will ask you to do to evaluate the tutorial. The thing that we've been doing today is a simplified approach to Bayesian statistics using this computational framework, using PMFs and suites, and doing everything using discrete hypotheses. So we always had a finite number of hypotheses. More generally, there are analytic distributions, so you can solve many of these problems by doing mathematics. It often comes in the form of doing lots of integrals. And if you pick up many Bayesian statistics books, the first few pages will be full of integrals. And if you love math and that makes total sense to you, great, that's a good way to learn Bayesian stats, but many people, I think, prefer no integrals. One of the nice things about discrete distributions is that all those integrals become for loops. And that for loop that we saw in the update function is a sneaky integral. Okay. The other thing that you'll see are numerical methods for solving problems like this. So that's a Monte Carlo Markov chain methods, and I'll say just a little bit about that when I point you to some resources. The reason I do it this way is exactly what I was saying a minute ago. I think this is a nice way to get started, to get this concept into your head, and then there are other ways of actually doing the computation. I also like this as an approach to problem solving, which is I start out using discrete distributions, non-analytic distributions, and I start out using brute force methods. What we did today is called a mesh algorithm. It's a brute force method of solving Bayesian methods by just enumerating the hypotheses. And that loop that we did, I'm going to loop through every hypothesis, I'm going to compute all the likelihoods, is a brute force solution. It works well if you only have 1 parameter, or 2, maybe 3, but the number of hypotheses starts to get really big as the number of dimensions gets big. So this doesn't hold up very well. But if you start out doing this, and your solution is good enough, you are done. But if you get to this point and it's not fast enough, well, you've figured out the hard part. You've got the model, you've got the likelihood function. Now you can do some optimization. You can break out analytic methods, you can break out numerical methods. Now you can make the thing fast, but you also have a reference. You have regression tests. Say, look, I know the answer, but it's slow. Now I'm going to optimize it and make sure I get the same answer. So this, I think, is a general good strategy for solving a lot of problems like this. Last thing I'll point you to, I mentioned my book a couple of times. This is Think Bayes. Most of the exercises that we did are in Think Bayes, along with a number of other case studies. You might notice there's a certain Boston focus I realized I've got the Boston Bruins problem, which is related to the World Cup problem. I've got the Red Line problem, which is the public transportation in Boston. So you can check out some of those examples. I also have a blog that's called Probably Overthinking It, where I do a lot of Bayesian methods like this, including one of my favorites, which is the rock hyrax problem. This is a generalization of the German tank problem. So you might find that interesting. Think Stats is a book about more classical data analysis, statistical methods, so if you're interested. And just so I'm not entirely plugging my own stuff, I mentioned David Mackay's book. This is available as a free PDF, and I highly recommend it. His chapter 3 is about Bayesian stats. Really interesting, nice introduction, especially if you want to make the transition from what you saw today to a mathematical version. Check that out. Cameron Davidson Pilon has a book that's called Bayesian Methods for Hackers. It's a free book on GitHub. He does Monte Carlo Markov chain methods. So if you want to make the transition from today going in that direction, that's an excellent next stop. And he does some of the same problems that I did. This is also in the slides, so you can look at it later, but here are a couple of other good resources if you're interested. And the last thing, before you're allowed to leave, you have 3 minutes. Please take those minutes to do a survey. This is very helpful to us. I was on the the tutorial selection committee this year. Having data from previous years really helps us make sure that we're selecting tutorials that are going to go well and be good quality. So help us out, fill in that survey. I guess the last thing I'll say is that there are 2 L's in excellent. So just if you want to put that into your survey, make sure you spell that right. It makes it more credible. Good. I will stop there. Thank you all very much. This has been great.